Hello. How's it going, Ethan? Feel free to ask me questions if you have any. We got, well, time's up, but I'm gonna give another minute just in case anybody's coming.
Okay. Are you lecturing today?
Yes, this is for my online 242 class.
Mhm.
So I'll be doing a full lecture, which more or less finishes chapter 21. Uh, but are you in this 242 class, or are you in one of my day classes?
I'm in one of your day classes. We're on chapter 4. I'm in
Oh, in chapter
physics
in
1.
physics 241. If I mean, if you have a question, I can answer it now, but you can also come back at like 6:30, and then I'll be available probably 6:30, definitely by 6:40. I'll be ready to take questions on any topic. But right, like I said, for the next hour and 20 or hour and 40 minutes, it's going to be roughly 242 stuff. But you're welcome to attend. I mean, it's not a problem. But like I said, if you have a question about chapters 1 through 4 or even 5, then you can come back at 6:30 if you want.
Okay, I wasn't sure if you were gonna lecture and go over chapter 5.
Uh,
Um,
Gotcha. I did start chapter 5 last night on my face to face, I mean, on my internet class. So you
okay.
can check out that video if you'd like. But what I did there was finish chapter 4, and then I got the three major aspects of chapter 5. I just introduced them, which was friction. I introduced a way where you can basically go about deriving your own centripetal acceleration. So that's about circular motion. And I also introduced them to air resistance and solved a body falling in a thick atmosphere, basically. So in other words, I've accounted for air resistance in a body that's free falling. But all that was
Okay.
covered, like I said, last night. It is on my YouTube channel already if you want to check it out.
Okay. And so will chapter 5 be due this Sunday?
Oh no, no, definitely not this Sunday. No, it'll be the following
Okay.
Sunday. Yeah. I've
Okay, I was
just
just making
basically
sure
started. Yeah, I get you.
because
It'd be scary, right?
yeah,
And the
yeah, when it
dates,
first
remember
showed
the
up
dates
it
on
was due
Pearson?
Sunday, so I wasn't sure.
Yeah, I will have to change that. But anytime we haven't, thoroughly covered a chapter, or especially if we haven't at least just touched on the chapter, there's no way the homework assignment is due that following Sunday. But like I said, it's such a long, drawn out process of changing the dates in Pearson that sometimes I get a little behind on that. So chapter
I
5
got you.
might be saying it's due, but it's not going to be due till next week.
Okay, I was just double checking because
No problem. Yeah, it's better safe than sorry. I appreciate you doing that, but
yeah. Yeah, thank you.
all right. Look, I finally got a 242 student. All right. Well, feel free to come back or hang around, whichever one you want to do. It's not going to harm you. It'll be kind of exciting to see all the math that we do in this particular class.
All right. Thank you.
You're welcome. Hello, Jen. How are you?
Good. How are you doing?
All right. I was just talking to a student who showed up for my face-to-face 241 class. Uh, and he's here. I think he might come back later, but he might stick around. But it's time to go ahead and get started. Are you ready, or do you have any questions before we get started?
No, I'm the only one here, aren't I?
Yes, you are. Oh, yep.
Okay.
The other guy
As
just left.
usual. Okay.
All right. Well, I'm going to go ahead and share my iPad screen. When we last talked, I introduced you didn't get to see it because I remember you had to leave a little bit before class was over, but
Yeah, we
hopefully
got
you
that
saw the video.
lab, so it takes me a while to get there.
Yeah, that's no problem at all. And in fact, there's a place at campus. I can get you a place if you want to do it there, so you don't have to uh, wait for the class to be over and then drive to the lab. There's
No, I have kids.
oh, okay, gotcha. Yeah, yeah, that's a whole different story.
Yes, it is.
All right, that's cool. Well, I'll go ahead and share my iPad screen, and we're going to start off where I left off last time. Were you able to watch the video from last time?
From where we left off?
Yes, ma'am.
No, not yet.
Okay, no, that's not a
The snow
problem.
days are killing me.
Yeah, I'm excited about it. I'm still a kid at heart when it comes to snow. However, a little bit of that kid died today when I tried to clear out our 9-inch deep snow driveway with a regular shovel. Uh, but I'm still not completely turned sour on it. I still like snow. All right. Well, what I
Get a
didn't get
sled, not a shovel.
to exactly that would be a lot more fun. All right. So what I didn't get to show you last time, but I think I just started to prepare to show you was a first a definition of an electric field. In other words, we were counting on uh, trying to get rid of the idea of action at a distance. So, as it was with Coulomb's law in terms of a force, which was given by K, Q1, Q2 over R squared, that works. But the problem is, it's as if, Q1 is reaching out across space without actually physically touching Q2 and applying a force to Q2, and then Q2 is doing the same thing. So what I introduced was the idea of one charge, and I changed the Q1 to just capital Q to be the one charge. So that one charge is what we're arguing is now the charge that's causing a disturbance of the space around itself. So all the space around the charge big Q, which used to be Q1, is now being pictured as if it's made a disturbance or an aura around that charge Q. Uh, but to keep from being hypocritical, which is a bad, bad, bad thing in science, we have to also ascertain that, or at least realize that if we decide that Q1 becomes big Q and all of a sudden uh, disturbs the field around it, there's no reason to assume that Q2 wouldn't also do that. So, in an attempt to still have that, what I did was I defined the electric field E like this. And I'm leaving a space on it for a reason, but E, the electric field, big space, is equal to what I'm now calling Q over 4 pi epsilon naught R squared divided by Q. And you see, if I divide out that Q, we now have a formula that's just uh, big Q over 4 pi epsilon naught R squared. So what we're doing is we're imagining just saying that Q over 4 pi epsilon naught R squared is what the big Q is making. And obviously, since the force was Q times Q over 4 pi epsilon naught, all we have to do is multiply the electric field that big Q makes by the charged little q, and that'll give us the actual force. I did put a vector symbol on it, so I guess it'd probably be best to leave it as if it's not a vector, but I really did that because I wanted to let you know that the electric field is also a vector quantity. We don't yet in this form have a way of showing it that it's a vector, but I'm getting ready. Well, I did last time, but I'm getting ready to show you that again. Now, as I said, the problem is if we argue that big Q makes a disturbance of the space around it, then it's obvious that little q does too. So the way we try to define it is we put a limit here. We say, oh man, I hate it when it happens. We say that a limit is going to be taken as Q approaches zero. Now, what I physically mean by that is if you're actually trying to, let's say, do an experiment to determine the electric field and test it to see if it fits this formula, you have to decide on how, well, you have to use equipment that dictates exactly how many decimal places of precision you could get. So you might say, for instance, we're going to analyze this electric field down to the third decimal place. And what you would do is you would use that formula, which is the limit as q approaches zero of QQ over 4 pi epsilon naught r squared divided by little q. So you'd get that same formula for the electric field, but what we do is do that with a test charge little q that we would bring in, and that would give us a force that we could measure, and then we take that force and divide it by little q, and if we get that little q or that force that we got that way is the same as the electric field we got this way, even to 3 decimal places, then we've made q small enough. The lowercase q has been made small enough. If not, if they don't match the 3 decimal places, we try a smaller test charge q, and we keep doing that until we get the precision that we need. So that's what that is about. In practice, we really just use the equation E is equal to F over Q, and we actually recognize it as a vector equation so that you can say F, the force, is actually just equal to the charge Q feeling the electric field times the strength of the electric field. And in fact, by this form, you should be able to see that the definition of the electric field direction is it's the direction in which a positive charge would be compelled to move if it was placed at that particular location. So when we go to solve for an electric field, we're going to solve for an electric field created by a charge big Q at a position P, a distance R away from big Q. So the electric field at that particular spot is uh, is what we're calculating. So in principle, all you really have to do if you wanted to know the force is whatever charge you put there, little q, you multiply that by the electric field, and you will get newtons. So if you look, for instance, the QQ over 4 pi epsilon naught r squared, we already found out the units of that were newtons. And of course, we just divided it by one of the charges, and we found out that charges were measured in coulombs. So clearly, the electric field has units of newtons per coulomb, and later we'll find that that's actually equivalent to volts per meter, which will be a much better unit to use. But the main thing is this equation is the way we use it in reality, even though this is a defining equation. So for instance, we should really list that as a triple equal bars because that's sort of the definition of the electric field. And we are going on the assumption, of course, that even big Q is still a point charge. If not, then the direction of the electric field goes from the center of charge of big Q to the point P at which we wish to know the electric field. Okay. So now that we've got all that out of the way, I'm going to go ahead and write down the result I got from vectorizing or making this a vector equation. And that result is the following. What we say is there's a differential electric field dE, and that's caused by dq over 4 pi epsilon naught. Now, what we needed was a vector that would point from the charge dq to the point P in space. And what I defined was in 3 space, I defined a vector RDQ that points from the origin of my coordinate system to the charge DQ. In other words, it points to the point at which the DQ is a point charge. And another vector R sub P, which points to the point P that we wish to know the electric field. So we had 2 vectors, R subscript DQ, and another vector R subscript P. And it turned out that the direction of the vector we wanted would be RP minus R dq. Now, the length of that vector is exactly the R that we're looking for in the formula. So down here, I'm going to put in absolute value bars because that means the magnitude of the vectors. I'm going to put R sub P minus R sub dq. And remember, Coulomb's law is a 1 over r squared law. But since I multiplied by the vector rp minus rdq, I've got an extra r on the numerator. So in order to cancel that one out, I've got to put a 3 down here instead of a 2. But that's the formula. Okay? Now, the big thing is, in order for you to use this, you need to know what these vectors are, and you also need to know something else. The other thing you need to know is that the differential charge element, dq, can be equal to the normal thing, if you're used to dealing with 3-dimensional charge distributions, is the 3-dimensional charge density rho, which would be measured like in coulombs per cubic meter, times the differential volume element dV. So you can see now that when you multiplied coulombs per cubic meter by dV, you should just get coulombs. But if it happens to have basically a 2-dimensional charge distribution so that you need not worry about the 3rd dimension, then you can reduce this to a charge density per unit area, sigma. That sigma, for instance, would have units of coulombs per square meter, and you'd have to multiply it by dA, where A is the surface area. So, coulombs per square meter times square meters would give you coulombs. And then finally, if you were dealing with something like we are in this example, that is a, sort of one-dimensional object, like a single wire that happens to be straight, then we use what's called the linear charge density, lambda, and that is given by lambda times dl, where lambda would be in units of coulombs per meter, and the dl, of course, would be in meters, so you'd get out a dq is equal to coulombs. Okay, so that's something we're going to use over and over and over again. I pointed out all that. I should probably take the time to write it. I'll do that now. The units of rho would be coulombs per cubic meter. The units of sigma would be coulombs per square meter. And the units for lambda would be coulombs per meter. Okay. And you can actually make them derivatives, so you can sort of look at rho as if it's dq over dv. And you could look at lambda as if it's dq over dl. In other words, a derivative of q with respect to L would be exactly what lambda is. All right. So now I'm going to go ahead and I'm going to draw a coordinate system that matches the problem here. It says an infinitely long, thin wire has a uniform linear charge density, lambda equals a constant, and can be imagined to lie along the z-axis of a coordinate system. Calculate the electric field at a distance r from the wire. So that's the problem we're setting up here. I notice I have two instances of the word a, so I'm going to erase this one. All right, and now I'm going to draw my coordinate system, and my coordinate system is going to be basically this. I should have drawn that a little neater, so let me draw it with this way. Okay, that's my z-axis. I'm going to cross it, of course, 1, 2, 3, 4, 5, 6, 7, 8, 9. Of course, I went 9. Okay, so that's now going to be 10. 1, 2, 3, 4, 5. We go right across here like this. And then there would be another one right here like that. This is my x-axis. This is my y-axis. And this is my z-axis. And always, when you're making a three-dimensional axis system, you should check it with your right-hand rule. Remember, your index finger pointing straight ahead should be the x-axis. Your middle finger pointing perpendicular to the index finger should be the y-axis. And then your thumb pointing perpendicular to both should be the z-axis, the positive z-axis. And you see that this one fits that bill as soon as I hold my hand like this, where my finger's pointing out towards me. Okay? Now, what I have is this infinite line charge, which means it's infinitely long. And I want to express to you that that's a thing we use in physics, but it's not literal. Like you don't literally have to have a wire that's infinitely long. In most cases, if you're say 1 centimeter away from the wire, then as long as the wire is at least 10 centimeters, the end is at least 10 centimeters from you both ways, then you should be good enough to assume it to be infinite. But a factor of 100 would be even better. So if you were 1 centimeter away and you kept it 100 centimeters from each end, then you would be even more correct in assuming it's infinite. Okay, so I'm going to put this wire along the z-axis like I'm trying to do here, and now I've got to do the other one as well. Okay, now what we're saying is this guy runs infinitely upward and infinitely downward. Okay, so it goes on forever. And what I'm also suggesting is over here is a distance r, because I said I wanted to know the electric field a distance r away from the wire. So that point right there, that is the point P. that I refer to in R sub P. Now, what I'm going to do here is I realize that this is an infinitely long wire that's also really thin. So I'm showing the thickness of the wire, but really it should be infinitesimal. And when you go to choose a differential charge element, it's usually best to choose it either in the first quadrant or on the x-axis or on the y-axis or on the z-axis or something like that. So that's what I'm going to do here. I'm going to imagine a little chunk of charge dq is right here. Okay. And notice that is on the z-axis and that its height would be dz. So in other words, instead of dl, I'm going to use dz. And notice that since it's along the z-axis, we can say the variable length from the origin up to that bottom of that test charge or that differential charge element, that distance is the variable z. Does that make sense to you? We're just going to say it's up a distance z because the z is the coordinate that gives us that. And then you're also used, hopefully, from calculus. Remember, they used to always say the integral from z to z plus dz. That's what we're talking about here. We're doing a z plus dz. So there's our little differential charge element. Its height is dz. And what I want to express about that is this quantity is called dq, and it's given by lambda times dz, where lambda is a constant. Okay, we're pretending we know lambda, by the way. We're also pretending we know r, and we're also pretending we know what dq is. Okay, so we'll work this all out sort of in terms of some total q or something like that, or in terms of a lambda, like we know that. Now, this vector, this little blue vector right here, its length is in fact z, but the vector itself is called r sub dq. Because remember, I said r sub dq is the vector that points from the origin to the charge dq. Now, can you guess what the formula for that r dq vector would be? You can use I hat, j hat, k hat if you want. Okay. It's a little it's one of those cases where it's so simple you doubt yourself. You see it's pointing along the z-axis, so we know its direction can be classified as the k hat direction. And then all we need is to multiply k hat, which is a unit vector, which literally means its length is 1 unit, not 1 meter, not 1 Newton, not 1 Coulomb, but 1 unit. So if we multiply that by z, then we actually have a vector of the right length. So the vector is just z k hat. That makes sense? All right, now I'm going to draw another vector. Let's see if you can do this one, for instance. This one's supposed to be RP, so it's supposed to point from the origin to the point P at which we wish to know the electric field. So this is our vector right here. I've already labeled the x-axis to give us some idea maybe of what the length of this guy is. Can you tell me what RP would be? Because this is R sub P, by the way. Do you have an idea what that vector would be? Or, you can use IJ and K hat as well, or no? Okay. Do you know how long it would be?
It would be R long.
Yep. And which direction does it point in?
I hat.
It would
No,
be the
J
J
hat.
hat,
J
exactly,
hat.
because it's Y.
That's I
So,
hat. X is I.
so do you think the vector would just be R times J hat?
Yeah, I was gonna say that, but
didn't have the confidence. That's okay. It's actually the number one problem. It's some of this stuff is so easy. You're like, I don't know what to do.
I thought I needed to know the other hat too. The X is
Gotcha. Yeah, you don't. In this case, we don't actually need the X hat, and we'll find out there's a lot of symmetries in this problem, so we can avoid a lot of the difficult stuff. So what I just did was I found out what dq is. dq is lambda dz. I found out what rp was. That's r times j hat, and r is a constant. And I found out what rdq was, which is zk hat. So now all I got to do for my for my formula is figure out what rp minus rdq is. Okay, and that's just straight subtraction. So I suspect you all know it's going to be r j hat minus z k hat. That's pretty straightforward subtraction, right? Now, it also helps to know the magnitude, and this is where we could use our knowledge of how to add two vectors when there or subtract one vector from another when they're tail to tail. Just in case you don't know exactly how to do that, I'm going to draw the vector on here this time, and it's going to be from here to here. It actually should be a little straighter than that, so I'm going to try again. So that's actually the vector that we're talking about. You can see that this vector, as I said, is RP minus R dq. Now that you know that that's the vector, can you maybe use the Pythagorean theorem to come up with a length for that vector? Because the bottom of the formula has the magnitude RP minus RDQ. So what do you think? Do you think you have an idea what that magnitude would be?
well, it's this square root of the square
That's it. That's it.
C and the square. Sorry, I don't know what to call them.
R. Yeah,
R, yeah,
exactly. Yeah, and it's not it's separated by pluses, not minuses, because the fact that it's negative just means the negative z is going to be squared. So yeah, you're absolutely right. It's the square root of r squared plus z squared. That's it.
yeah. Okay,
Okay, makes sense?
easy peasy. Mm-hmm.
Easy peasy. Right, exactly. So now what I'm going to do is I'm going to erase where I drew that P because it seems like space is pretty slim. Oh, Nelly, don't know why I did that. We don't have as much space available to us as I would like, so I'm going to write that P somewhere else right after I scratch out that color. And what I'm going to say is P is that point right there. Okay. Now, what I want you to notice is each vector DE is actually going to be parallel to that green vector. That's the whole point of us, making the vector that we did. And from that, you can see that DE might be something like this. For this particular differential mass element, we expect, or excuse me, for that particular charge element, we expect this to be DE. Uh, if we considered another charge element down here, a distance z below the axis, that would create a similar dE vector like this one that would actually be exactly the same magnitude, but in sort of a mirrored direction. So, what do you think happens to the x component of that dE? Do these two x components cancel each other out, or do they increase the total?
I think they might cancel.
Okay,
But,
and you're talking about the x component or the y component? Or excuse
sorry,
me,
okay.
I should say the
DE.
y component or the z component. My fault.
The one that's the dotted line, is that this?
That's the actual vector. And then the component would be either parallel to the y-axis or one that's parallel to the z-axis or
Oh,
parallel
then
to
they
the
would
negative z.
increase it.
Yeah, so exactly. The y-axis is going to be increased by these two,
Yeah.
whereas the z component is actually going to cancel each other out.
Okay, yeah.
Does that make sense?
Yeah.
So we expect that physically, but we're also going to see where it comes out mathematically. So I just wanted to let you know, for instance, you can call that angle right there theta,
Mhm.
and that angle right there is the same angle theta. And you can see that the dE times cosine theta would give us the y component, and then the top one would give us the same y component, but the dE sine theta for this one would be a negative, and the dE sine theta for the one for the bottom just DQ would actually be a positive. So those two would cancel each other out. So we expect no, I think I said Y again, but we expect no Z components.
It's the Z that cancels out and the Y that
Exactly.
increases.
Exactly. So by symmetry, we expect, actually, I should write it this way. Actually, I should just say DE instead of both of them. I should just say just plain E. We expect E to only have a Y component. Okay, so now I'm going to go ahead and work out my problem. E is going to be equal to the integral of dE, and I'm going to go ahead and pull out everything in front that's constant, and of course that's initially just 1 over 4 pi epsilon naught, like that. And then we have the integral, which is going to be times lambda dz of parenthesis r j hat minus z k hat, like that. And then all of that will be over. Remember, the exponent was 3 in the bottom, not 2. So it's going to be r squared plus z squared to the 1/2 power. That's what a square root means, but we're going to cube it, so it'd be to the 3/2 power. Now, getting that filled out that way is really warrants you earning the whole 99% of the points for solving this. The rest of it's just math. But like I said, it's we have multiple choice, so it might not be that easy. But I do want you to practice this. Now we also know the lambda is a constant, by the way, so I'm going to pull that out in front in the next step. But right now, what I see is I'm definitely going to need a trig substitution to complete this integral. So I'm going to write equals lambda over 4 pi epsilon naught, and then I'm going to put a curly bracket over here, and I'm going to say j hat, because I hat, j hat, and k hat are special unit vectors that have no derivatives. So, for instance, you don't have to integrate them or differentiate them. You just can pull them right in front because they're constant integrals, or constants vectors. So you don't have to do anything with them. Whereas if you use the r hat vector or the rho hat vector or the theta hat or the phi hat, all of those are actually functions, and therefore you'd have to take the derivatives or the integrals. In this case, you don't. So what I did was I just took the rj hat and I put the j hat out in front, and what I'm left with is r dz over r squared plus z squared to the 3/2. That's one of the integrals. In fact, that turns out to be the j hat component of the vector. which we said is going to survive. Now I'm also going to do the minus part, so I'll say minus, and remember z is actually a variable, so I can't pull that out in front, but I can pull the k hat out in front. Oh, and I should probably put that integral back in there. Forgot that part. Uh, put the integral back in here. Now in this case, I have a z dz over r squared plus z squared to the 3 halves. So that's the two integrals we got to do. What I'm going to say for this one is let z equal r tangent theta, then dz is equal to r secant squared theta d theta. Sorry, I wrote that really small, but I want to make sure you can read it. So I said let z equal r tangent theta, and therefore dz would be r secant squared theta d theta. Okay. With this other one thing you might notice is we're going to integrate basically from negative infinity to positive infinity. Same thing here, negative infinity to positive infinity. That's what we call a symmetric range. Like if I integrated from -1 to +1, that would be a symmetric range, or -3.4 to +3.4 would be a symmetric range. The reason why I bring symmetry into this is if you look at the integrand of the second integral, the r squared plus z squared, that's automatically even because if I replace z with negative z, it's squared, so it's not going to change anything. So r squared plus z squared doesn't change at all when I change z to negative z. But I do have a z on top that's part of the integrand too, and that makes it an odd function. And whenever you integrate an odd function over an even range, it automatically turns to 0. Okay. The archetypal even and odd functions being sine, which looks like this, going right through, oops, looks like this going right through the center. My center wasn't so well drawn though. Okay. So what we're supposed to be seeing is the left-hand side is a mirror image of the right-hand side, uh, an upside down, I should say, mirror image of the right-hand side. This is what we call an odd function. And if we looked at cosine, it would look like that. That's an even function, and that's cosine. So, as I said, this function right here is odd, implies integrates to 0, and that's why, like I said, we don't expect any k component to come out. You could easily do this integral because all you have to do is let u equal r squared plus z squared, then du would equal 2z, and you already got a z on top, so you could actually do that integral very easily. It just become the ln of r squared plus z squared, but then when you go to actually evaluate it, it's going to get 0. So all we have to do now is the first integral. And I'm going to continue that way by writing out. Notice now that I have the r, which is a constant. I can pull that out in front too. So now I have lambda r over 4 pi epsilon naught. And then that is times the integral of, this is the neat part. I'm going to factor out the common factor of r squared, and then I'll just get 1 plus tangent squared theta, all of which is to the 3 halves power. That's the denominator. The numerator is r secant squared theta d theta, like that. So now you can see that The r in the top next to secant squared, that can come out in front too, and that's going to make a r squared in the numerator. And here's the cool part: the r squared in the denominator, that square is going to cancel out with the 2 in the denominator of the exponent and leave it with r cubed. So ultimately, we'll have a r squared on top and an r cubed on bottom. So it's just going to become lambda over 4 pi epsilon naught r, because all but 1 will cancel out. The other beautiful thing, of course, is 1 plus tangent squared is secant squared, which was the whole reason that we made this substitution to begin with, because we wanted that nice little cancellation to work out. So my next line is just going to be lambda over 4 pi epsilon naught r. And what we have now is the integral of secant squared theta d theta divided by, now remember, just like the r squared was in the bottom, we now have secant squared in the bottom. So that's going to become secant cubed in the bottom because it's raised to the 3/2 power. So that's a secant cubed theta in the bottom, which is secant squared over secant cubed is 1 over secant, and that's, of course, cosine. So I'm going to write this. Oops, I left out my j hat. So let me put that back in right here. See where I just put the j hat vector? Putting it in here too. Putting it in here too. I'm going to say lambda j hat over 4 pi epsilon naught r times the integral of cosine theta d theta. Now, if you look at our trig substitution, we did z equals r tangent theta. That's exactly what we see on the actual diagram to the left. So when we look at that, we can say, oh, okay, as z goes to positive infinity, theta goes to what angle is that? Do you know?
No, sorry, I was writing.
Okay. So
I can
what I'm saying is if you let z go all the way up to infinity, that theta is going to approach what angle? Could you see from that diagram? Or might you guess? If you stand at the base of, let's say that tallest building in the world, I think that's the one in Qatar now. If you stood at the base, would you have to aim your head straight up to see the top of it, or real close to straight up?
Yeah.
Yeah, it would be 90.
Yeah.
90?
So
Yeah.
yeah, we're going to integrate it from negative 90 to 90, which is of course negative pi over 2 to pi over 2. I forgot you were here, Josh. Sorry about that. So that's our range of integration. Now that we have that, I know that the derivative of sine is cosine, so the integral of cosine is sine. So now I can finally write that I have lambda over 4 pi epsilon naught r times, now it's going to be the sine of pi over 2 minus the sine of negative pi over 2. And all of that will be times j hat. Okay. Sine of pi over 2, of course, is 1. Sine of negative pi over 2 is negative 1. Minus a negative is plus a positive. So my final answer is E is equal to lambda over 2 pi epsilon naught r in the j hat direction. Any questions on that one? So that one looked like it could be a really horrible problem, but luckily we had various symmetries that worked out for us. It happened to be one integral that is easily solved with a trigonometric substitution. that sort of thing. What I recommend you guys doing, obviously, is try to solve this problem all by itself. Imagine watching it, trying to make sense of it, pausing it as many times as you need to while you're watching it, and then try to do it without using the video. When you run into a snag, then you again stop solving the problem, go back, watch the video a little bit more, turn off the video, and then try it again. Maybe starting from the same place you were on, or you could start over, either one. But do that a couple times and you'll probably be able to get it. Then, what you might want to try, which I think is extremely interesting, is instead of making this thing infinitely long, you could actually integrate it from negative L over 2 to positive L over 2, and then its length would just be L, and you'd get a different formula than the one we got for infinite. And one of the extra credit things you can do for this class is to see exactly how large L needs to be for R to be, like 1 meter or something. And say you want it accurate to two decimal places. Exactly how much bigger does L have to be than R for the infinite formula and the correct formula to give you the same answers to two decimal places, maybe even to three decimal places, that kind of thing. So those are all really good ones. Another one that's kind of neat is I said first you could imagine it only going from negative L over 2 to positive L over 2. You could also try solving it from, let's say, negative L up to 4L. So it wouldn't even be symmetric. Then you'd actually get that z component would come back in. So you could actually carry out that integral, which I've already told you how to do. You just have to do the substitution u equals r squared plus z squared. So you can totally do it. But if you can do that, then you'll be more than prepared, because this is literally the second hardest problem we'll have in this entire course, in my experience. Okay. So it's not going to get much harder than this, and really it's really crazy because the one that's the hardest is exactly the same integral. The only difference is we have to do a cross product in the integral, which is ugly, but it turns out you can do that pretty well too. Any questions before we move on to our next example? All right. Well, I actually skipped a page because sometimes I need more room, but this time it seems like I was able to pull it off and the room allowed and didn't have to write anything too terribly small. So again, if y'all need to see any of that, that's what that looks like. That's our substitution and everything. And I know this answer is actually right, by the way. I've been working with it a long time, but it is interesting to see that when we have a point charge, the distance dependence on the strength of the electric field, it goes like 1 over r squared. But when we have an infinitely long one-dimensional charge, it goes like 1 over r. Later today, in fact, we'll show you that when the plane is infinite instead of a single one-dimensional object being infinite, you actually then have an electric field that doesn't depend on distance at all. In principle, it's going to be the same strength no matter how far away you are from the plane. So that's kind of cool. Let's move on to the next one I call example 2. It says a thin loop of wire of radius big R has a uniform linear charge density lambda equals a constant. What is the electric field a distance z, I left out a n in there, a distance z above the center of the loop and on the loop's continuous symmetry axis? There's actually more than one symmetry axis for a loop, but there's one that's continuous, meaning the one right through the middle, like your finger going through a wedding ring. You can rotate that wedding ring by any angle, and it will always look the same, assuming it's a symmetric ring like this one is. Okay. All right, so let's draw a coordinate system again. This time, it turns out that the x and the y are both important. So I'm going to do it like this. And I'm going to do it like this. Okay, so this is going to be my, oops, I forgot it. I got to take it off, nice, neat drawing to write an X and to write a Y and to write a Z. Okay, now my ring of charge, I'm going to draw in black this time. And I'm going to say it goes like this. Ooh, I don't know how I got drawing on that form, but anyways. So something like that is supposed to be an oval. I did pretty good, but not great. So anyways, we're going to assume that is a circular loop of wire.
It's okay. We're not getting our degree.
Yeah, exactly. It still bothers me though. I can't stand that it came out that bad. I do so much better on a chalkboard, but oh well. We'll suck it up. Okay. So that is going to be our loop of charge, and it's got, charges embedded in it, just like the infinite line charge did. Only this one, of course, is stretched into a circle, and it's only a finite length. But we do want to know the electric field strength, a distance z above the circle. So that's where I'm talking about wanting to know the z. Now, what I do know is this. I can, for instance, take this little angle right here, which you might recognize as the theta from the polar angles or from the polar coordinate system. It's also the theta from the cylindrical coordinate system, and it's also in many cases the theta for the spherical coordinate system. But the main thing is, if I go over an angle theta and then allow that line to vary by an angle delta theta, then I get this little wedge of pi shape, but it's not really, an object. The thing is that I've now chopped out sort of a small piece of the charge, and this is what I'm going to call dq. And we know from, trig, when we introduced radians, that the arc length s is given by the radius r times the angle theta in radians. So this dq is going to be lambda times dl, but the dl is going to be r d theta. So it's going to be lambda r d theta. That's our differential charge element. Uh, Now, the hard part is we actually need a vector pointing to that. So I'm going to take this red vector right here and say that this vector is r dq. Now, this is one that I would normally, like I said, ask you folks to tell me what it was, like I did in the last one, but it's a little harder, so I'm not gonna not gonna beat you up with that one. But feel free to guess it. Uh, I will tell you that we are going to use the angle theta and trig functions, so that might help you. But more specifically, it turns out to be r cosine theta I hat plus r sine theta j hat. That's the r dq vector. Now we also need the rp vector. Remember, I'm using this formula right here. Joshua, we covered this last time, and you weren't here when I went back over it again. But just a reminder, rp is the vector that points from the origin to the point P at which we wish to know the electric field. rdq points from the origin to the differential charge element. And then once you have that, you can fill out everything else. I'm going to take and say, draw a red vector that points up to P. So this vector right here is RP. Okay. So anybody think they know how to write RP with I hats and J hats and K hats? Josh, you think you got it? Or Jen, how about you?
Is it the same as before?
Yep.
Yeah, it's only K hat.
Sorry, I was
Yep.
pulling a dish out of the oven.
Gotcha. So it's a Z K hat is what we want for RP. That also tells us that RP minus RDQ is equal to z k hat minus r cosine theta I hat minus r sine theta j hat. Now, if you look at that, that might be a little scary to figure out what its magnitude is, but if you remember what the vector looks like on the actual picture, you can probably immediately guess what the length of this vector is. I hope you can. But if you can't, that's okay. You will after I tell you. So there's the magnitude. Anyone want to take a guess? I'm going to draw the vector in purple here. It's actually going to go from P to this guy. So that's the actual RP minus R dq. It's got a length. One leg is the vector RP, and the other leg is the vector RDQ. So I think you can figure out what the magnitude of that is.
Pythagorean theorem.
Yep, Pythagorean theorem. And because the r cosine and sine are in there, what you'll see is the trigonometric identity sine squared plus cosine squared equals 1 is going to get
Yeah.
it to reduce to this. But yeah, it's just going to be the square root of r squared plus z squared. Okay, and I don't know why I wrote it in purple. Well, I do know why I wrote it in purple because I wasn't paying attention, but evidently I'm writing it in red. Okay. Now, for some reason, I was actually planning on doing the solution in an entirely different color than this, but I didn't. So let's go on. Solution. So again, we've already started the solution. I just didn't write down the words yet. I've already given you an idea by pointing out the vector before. So we now know that our formula is E, which is equal to the integral of dE, which is equal to lambda r over 4 pi epsilon naught, and integral, remember dq was lambda r d theta, so that's why you see the lambda and r came out front. So now all I got left up top is d theta, and then times the vector, which would be z k hat minus r cosine theta I hat was supposed to be that one, minus r sine theta j hat. So that's the vector that gives us the actual direction. And then all of that would be divided by r squared plus z squared, which remember it has a power of 3 because we had to make it squared, but there was already a power of r in the numerator. So to cancel it out, we had to put a third one down here. Now, the big thing is we can see right now that this little dE vector is this guy. Now, if we look back here, I think you'd see that we'd have another dE vector which has the opposite x and y components as the first dE vector, but the actual z component is going to be the same in both of those. So do you see that the I hat and j hat by symmetry are going to disappear?
Yes.
So that's a way we can completely avoid this. You could miss it, and then you'd still have to carry out this integral, but the integral is actually still doable. It's just kind of ugly and not fun. But yeah, we can now say that the I hat term and the j hat term are going to integrate to 0. So I will write that as follows: by symmetry, the x and y components of E will disappear. Uh, I just realized I can't remember how to spell disappear. I want to put like 16 S's and 14 P's in there. Anyways, will disappear or integrate to zero. All right. Now that we have that, we can just deal with what's left, which is E is now equal to lambda R Z over 4 pi epsilon naught integral. Uh, I wrote dq up there. That was supposed to be d theta. Let me correct that real quick. Hopefully y'all remembered it because I said it. I remember saying it properly. I just didn't write it properly. So this top is now just going to be d theta, and the k hat can come out in front, but I think it's a little neater to just write it there right now. It doesn't have to do anything with the integral. I can pull it out in front of the integral at any time. But now I have the same old conundrum at the bottom, which is the fact that I have an r squared plus z squared. But in this case, both the r squared and the z squared are constant. So that turns out to be nothing at all. Sorry, it took me a second to realize that. And this is to the 3/2 power, not to the 3 power. All right. So now I can say equals lambda r z. Let me go ahead and put the k hat out in front now that I've more or less completely finished everything. Over 4 pi epsilon naught r squared plus z squared to the 3/2 power. And then all I have left is an integral from theta equals 0 to 2 pi of d theta, which obviously just gives me 2 pi. And I get that the electric field is therefore equal to lambda. Now, this is a smart way to write this. I was going to take that 2 pi that this integral is and cancel out with the 4 pi, but notice if I write lambda and then write the 2 pi that I got from the integral next to the r, that 2 pi with that r there might remind you of something related to the physics problem. Anybody know what 2 pi r would be?
Circumference.
Yes, it's the circumference of the wire. And since you're multiplying the circumference of the wire by the charge per unit length of the wire, you get the total charge of the wire. So lambda times 2 pi r is literally the total charge Q. So I'm going to say assume total charge is Q. So now all I have to do is just down here, I'm going to write, make sure I get my red marker. I'm going to write r squared plus z squared to the 3/2 power times k hat. And that is the right answer, but not necessarily the way I want to write it. So let me rewrite it again. I'm going to say E is equal to Q Z over 4 pi epsilon naught r squared plus z squared to the 3/2 k hat. Okay, so that's the actual answer. And you can actually see if you wanted to look at this for cases where z is much, 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 much bigger than r, then you could actually uh, either expand this in terms of z over r or r over z, and then erase the higher order terms. And what you'd see is you'd ultimately get that this electric field is acting just like a point charge of charge q. So you'd get a 1 over r squared sort of thing going on. You can sort of look at that as if the z squared being way bigger than the r squared means the r squared plus z squared is essentially just z squared. So z squared to the 3 halves would be z cubed. Then you'd have z on top with a z cubed on the bottom. So it just becomes q over 4 pi epsilon naught z squared, which is the 1 over r squared law of Coulomb. So that's kind of cool. If you came up closer to it and you imagined a z much smaller than r, you would probably get very, very close to zero. And in fact, it would ultimately be zero at the origin. So, any questions on that one? All right,
Nope.
let's try for another. Now, this one is going to be a little bit different. This will be example 3. And in this case, I'm going to draw a coordinate system just like the last time. And I'm going to draw a disk again, only this time instead of it being circular because it's a loop, it's going to be circular because it's a disk. So this is going to be my z-axis, my x-axis, and my y-axis. And I'm going to say that this is this side, and this is this side. So that looks, I guess, a little better than the last one, even though it's, still not great. All right, so there's a disk. Now this is let's say find the E field, a distance z above the center of the disk. The disk is uniformly charged. Okay, that's really all I have to say. And to you, when you see that the disk is uniformly charged, you should immediately think, okay, this is a disk. That's a two-dimensional object. The two-dimensional charge density is sigma, so I'm going to say sigma is a constant. And that's exactly what we're doing. Okay. If it were an infinite line charge and I said it was uniformly charged, you'd say, okay, well, a line is one dimensional. Therefore, I want to use lambda, and lambda should be a constant. If it was actually a three-dimensional charge distribution, like a spherical distribution of charge, and we told you it was uniformly distributed, what you would say is, okay, obviously this is a three-dimensional object, so the charge density is a rho, and that rho should be a constant. Meaning, if you open up a 1 cubic centimeter cube of the sphere and found it had 84 nanocoulombs, if you grab any other millimeter cubed section of it, it will also have 84 nanocoulombs. Okay, so that's why all this is this way. Now, this one does have a radius r, and like I said, it'll have a surface charge sigma. So that's what I'm going to go with on this one. Only this one I can't use my special formula, but I can use the result that I got here. E is equal to dq times z over 4 pi epsilon naught r squared plus z squared. So I can say solution dE is equal to, I'm going to say z dq over 4 pi epsilon naught r squared plus z squared to the 3 halves, and it's going to point in the k hat direction. In other words, I just took a differential of my last answer. Notice I have to imagine dicing this disk up, or at least the surface of the disk up, into circular loops. So let me show you what that looks like. I'm going to come out here, and then I'm going to come just inside of here. And this is going to be a radius R. And this is going to be a width dr. So that this sort of looks like a circle whose inner radius is 2 pi r. So in some sense, you might think dA is 2 pi r times dr. Now, in reality, it's actually smaller, or it's actually a little bit different than that, because what you really need to do is basically take a sphere of radius, or excuse me, a circle of radius 2 r plus dr, and take the area of that, and then subtract from it the area of the inner circle, which is a circle of radius pi r squared. When you did that, you'd see that there's a couple other terms in this thing, but those other terms are on the order of dr squared or dr cubed or something like that. So that's why we ignore them. My YouTube channel has a discussion of that if you need be. But basically, we're just going to say that dA is 2 pi r dr. Therefore, we're going to make the argument that dq, oh, excuse me, that dq is in fact sigma times dA, which equals 2 pi r sigma dr. So now we can say E is equal to, I'm going to pull the k hat out in front, and I'm going to put it over top of 4 pi epsilon naught. I'm going to integrate.
Wait, did you
Uh,
just carry the sigma over to the other side?
I haven't written it in there yet, but yeah, I
Hold
did. I did in the DQ expression. Yeah, absolutely. I just
on.
haven't put it in the integral expression yet.
Oh, you okay, you multiplied sigma on both sides. Never mind.
Yeah, gotcha. And the Z should be able to come out in front as well, so I'm pulling that out. But the DQ, I'm now going to replace that with 2 pi r sigma dr. And then in the bottom, I've got r squared plus, let's actually make it z squared plus r squared. I think that might make the integral process a little more transparent. And that's to the 3 halves power, like that. Now, if you look at this one, this integral is actually doable because I have an r on top. So I can pull out the 2 pi and the sigma out in front, and I'm going to say 2 pi sigma z times k hat. All that's going to be over 4 pi epsilon naught integral. Now the dr, or what we have left on top, is r dr. And then in the bottom we have z squared plus r squared, oops, plus lowercase r squared. All that to the 3 halves power, like that. So what I'm going to do is let u equal z squared plus r squared, which implies du is equal to 2r dr. So I'm going to grab this 2 and put it with that r to make 2r dr. And these two pi's can cancel out, and I'll just be left with a 4 on the bottom and the epsilon 0 on the bottom. So now let's continue. I get the pi's canceling out, but I still have a sigma z k hat on top, and on the bottom I have a 4 epsilon naught, and I have now Since I borrowed that 2, that became 2RdR, which is just du. Excuse me, that's a du. It looks like an N over u to the 3 halves. Of course, that's basically the integral of u to the negative 3 halves, and the integral of u to the negative 3 halves is u to the negative 1 half divided by negative 1 half, which is basically negative 2 times it. So I'm now going to say we've got sigma z k hat over 2. Notice the 2 came back to us. That's why I canceled out the 4 and made a 2 at it. But we also got a negative back as well. So I'll just leave that negative out in front. I've already dealt with the 2 coming up from the integral. Now all I have left is z squared plus r squared to the negative 1 half power. And that has to be evaluated from r equals 0 to big R. So when I do that, I get sigma z k hat over 2, oh, and there's a negative still, over 2 epsilon naught. And then when I take the r squared case, it's going to be r squared plus z squared in the bottom under the square root minus 1 over, and it's technically going to be the square root of z squared in the bottom, which is just the absolute value of z, like that. And that's the actual function, but I don't like that negative being out in front. So what we can do is I can go ahead and write e as if it's equal to sigma over 2 epsilon naught times, now I'm reversing the order, and in fact I'm multiplying through by z. So z divided by the absolute value of z just becomes 1, and it was negative, but now it's in the front, so it's going to be a positive 1 minus, I guess I should just write it as z over the square root of r squared plus z squared, like that, and then times k hat. So that's the answer to that one. Any questions on that?
Nope.
Now, if you do imagine this one where z gets really, really small, so if you imagine z becoming or approaching 0, what you'd end up getting is basically just the sigma over 2 epsilon naught, and that turns out to be exactly right. That's what you get when you find the electric field of a infinitely large plane that has a charge density sigma. The electric field will be everywhere perpendicular to that plane, and will, if assuming sigma's positive, it'll point away from it, and it has no dependence whatsoever on distance. So that's what I was talking about to you earlier. A point charge, the electric field falls off as 1 over r squared. A infinite line charge, the electric field strength falls off as 1 over r, and an infinite plane of charge, the electric field does not fall off at all. It's like you can't get away from it. And that's, if you've seen, episodes like what was, I don't know, the basically the season or the starting episode of Star Trek Next Generation, it's entry or something at far something. But anyways, they ran into this ginormous wall in space, and everywhere you moved, it didn't like feel like you were getting any closer to it. That's what's going on here. You've got something that's infinitely tall and infinitely wide. If you move back, you're still going to see it infinitely tall and infinitely wide, so it don't feel like you get away from it at all. That's why, for instance, if you go into a lab, you might find a very bright all filling light in the room, and that's because they've taken usually a series of the tube lighting, that fluorescent tube lighting, and then they've covered it up with a plane, if you will, of diffusing material. So like it's often a random plant pattern of clear plexiglass or something like that. That makes that whole window hole act like an infinite plane, at least close to it, so that all of the light is essentially equally bright, whether you're really close to the ceiling or close to the floor. If you just had the strings of light, you would find the brightness of the light falling like 1 over R. So when you're 1 meter away, it would be a certain brightness. But then if you got 2 meters away, it would be half as bright, and 3 meters away, it would be a third as bright. This makes it more like even if you go 1 meter away or 10 meters away, it's always going to be the same brightness. It's not really true because obviously, once you get 10 meters away, those planes of light no longer look like they're infinite. So that's a problem that you're not going to overcome. But the more of them you put, the more like a infinite plane it is. So remember that the point charge falls like 1 over r squared, the infinite line charge falls like 1 over r, and the infinite plane falls like with no dependence on r. So I didn't get to do as many as I liked. There are a couple things that they tell you about dipoles. So an electric dipole is two equal but opposite charges set a distance d apart. And if you take the charge of one of them as a positive number and multiply it in coulombs by d in meters, you get what's called the dipole moment. And it's basically given by the formula QD, and it's a vector, only it points the opposite way that the electric field would. So remember, a dipole is made like of a positive and negative charge. I want to explain this to you really quick. So here's the positive charge, here's the negative charge. This distance is d. This charge is negative q. This charge is positive q. What we represent this as is a vector that points from the negative charge to the positive charge. That's the dipole moment vector, and it's equal to q times d, where d is like the length of that little vector we see there. Okay, so that's the dipole moment. And when you work out the problem, what you'll discover is that the torque on a dipole moment is equal to P cross E, and the energy stored in a dipole is equal to the integral of, well, we don't have to actually say integral. That's how you derive it, but you just say U is equal to P dot E. In other words, a dot product. So that's the two major topics you need. I'm not going to make the chapter 21 homework due this Sunday. It's going to be due at least Tuesday of next week. But you guys are free to go, and I'll wait for the last person in case y'all have any questions.
Did you make any announcements at the beginning of class?
Nothing, but remember, you do have an online test that's due Sunday. Uh,
Yep.
there was going to be chapter 21 due Sunday, but I think chapter 20 was due either just recently or it's going to be due tomorrow or
Okay.
Sunday or
Okay.
something. So just keep an eye on that. But you have an online test that's due Sunday. You get up to 3 attempts, only your highest score counts. And then the following week, a week from or next week, you're supposed to do a face-to-face test. So you've got to find a proctor or show up on one of my classes.
Okay.
Okay.
And you said that's yeah, that's not what that would be the following week.
Yeah, the following week. Yep. So you'll have that whole week to do it. So you just got to find something that fits in your schedule sometime between Monday of next week and Sunday of next week.
Okay.
Okay.
All right. Thank you.
All right. See you, Josh.
Yep.
How
Have a
about
good
you?
night.
You too. How about you,
Thank
Jen? You
you.
need anything?
No, I was just listening.
Okay.
Thank
Well, make sure
you.
you get your test done. You know, if you have questions before then, you send me a text. That's probably the easiest way to make sure you get up with me. Emails work, but like I said, it's not easy for me. I always check them. So, especially if you sent me one and you don't hear back from me within a day, then you might as well go ahead and text me.
Okay. All
Okay.
right. Thank you.
All right. Thank you. See you, Jen.
So, yep.
Bye bye.
Bye.
Okay, that's in there. There we go.